Ready? And week number 2. Pretty soon we're into week 5, which is like already 1/5, 20% of the way through the semester. Moving fast. There was like, I think I ended up with like 10 or so emails about module 0, like gone, just disappeared. There was nowhere to submit. Homework 0, quit, yeah. And then when I checked it, it was just there. And I didn't do anything. It's not like I went in and changed settings or anything. Very weird. But just to reiterate and kind of, oh yeah, go ahead.
I even went with TAs too, and they said that they reopened it. And it's like an archive itself or something.
Archived itself. Weird. Okay. Yeah, that's always a feature that you want. It's just self-archiving information. But in general, there's no penalties for late submission. So most of the assignments are due like midnight on some day. If you're turning it in at like 3 a.m., that's not late. Like it's there before anyone is ever going to see it, and there's no late penalty. So you don't have to ask permission at midnight. Like, oh man, I hope he's still checking his email. Like, I will not be checking my email. I'm asleep at like 9 p.m. these days because I wake up so early. Like I can't. Just something changed. My brother calls it dad mode, of just like a switch got flicked on, and now every day it's like 6 a.m. I'm up making scones, making coffee, like just ready to go. So you don't have to ask for permission. The only time that I ask you to like give us an update is like if it's going to be 3 or 4 days late, like it's days later, and someone might be looking at these to try to give grades. Put a note in there so that TA knows it's coming. Like, hey, it's not here today, but you know, by Friday, or yeah, in this case, like by Monday, I'm gonna get it done. I just need the weekend, and that's totally fine. So the 2 things we need are when are you gonna submit it? Then second part is what help do you need? So if it's just time, that's easy. You can take the time. But if it's like conceptual stuff, then let us know, like, hey, I'm going to class. I have a question about this. I'm going to talk to Professor Cooper, or office hours are on Thursday. I'm going to come and ask about this thing to finish this assignment. Make sense? This is like practicing professional courtesy, because yeah, people talk a lot about like preparing for the real world. Like, this is it. This is the real world. Welcome. Like, you made it. And so just practicing like treating each other courteously, and if it's going to be late, things happen, just let us know. What's the plan? What's the next step? And today, my plan was jumping into like module 1 homework. I didn't expect like module 1 readings to be done or anything. But so far we've done, hopefully the quiz felt like it was a review, kind of doing a free body diagram, Newton's second law. And then that homework 0, where we were doing our first like Jupyter notebook, probably felt like a whirlwind of like bad memories or lack of memories of like, at least most people that I've talked to, it's kind of like they took CSE 1010 and then the next 700 days just desperately tried to forget the whole experience. And that seems to be, not everybody, some people are like, this is the best, I'm gonna double down on programming efforts, but not us. We're mechanical engineers. We're like, give me a wrench, give me some cables, 3D printer, some of that stuff. So that was like as much Python probably more than we need for most to get like base level projects done. So you did a little bit extra work, I created some code, debugged a little bit, and we won't need much. That's about the level that we need for all the projects. So if you can get through that, we can get through projects and then work on the physics involved. Cool. Ready for chapter 1, problem 1. Or there's still other questions? No, we're good? All right, we'll jump right in. So in the syllabus, well, and even the reference, like if you look at reference material and readings, there's always a link to the chapters that we're using. So in this case, we have chapter 1, chapter 2, and if you follow that link, because we're here on UConn campus, it'll jump you right into a PDF version of the textbook. So I'll scroll, I'm gonna skip over the reading part and jump right into problem 1. And I'll leave this kind of big. So in this problem, we have a coordinate system labeled for us, and then there's a box sitting kind of on that EX, EY floor, and we want to figure out where is point P. What kind of problem is this? It seems kind of static, right? Like it doesn't seem like a dynamics problem. So what are we doing here? Yeah.
Seems like some geometric.
Like geometric, right? Yeah. So we're using geometry to describe like locations and positions. So that general process is called kinematics. So here we're trying to define the kinematics of this point P. And there could be cases where it's the same exact problem, but now the box is rotating. So we want to track point P, and we know where it is to begin with, but now it's spinning, so where is it now? So like at what point in time? At a different point in time, where did it go? So that's our first step. Where is point P? How do we describe where that is? And this one, I want to see like how you do it to see what we should talk about to start. So give it a shot. Where is this point P? And I'll try zooming in some so we can see it a little better.
mean, what's your question? Yeah. Oh yeah. Okay. Yeah, we're doing some physics here.
All right, so I've seen most of the things that I've seen are kind of like something like this. What is that? 6.98. Saying like that position P is these three coordinates, something like that. Yeah. But also, we could say have you seen this before where you have like magnitude and unit vector added up like that? A little, some ringing a bell a little bit. Are they different? Like, are these describing different positions of point P? No, it's the same. Like the vector is the vector. Like once we say like we're starting here, going to here, saying RP slash, really it's P slash O. So if you're saying like RP, you're hopefully there's only one origin that you're talking about. So I'm going to write out explicitly that it's P slash O. So this one's a little bit better, at least for dynamics, because a lot of times you'll have more than one coordinate system, or maybe like a coordinate system that is moving. And there we want to be very, very explicit about like, where is this unit vector pointing? What is a unit vector? Like I'm using that word, but what it, yeah.
Like we're like the magnitude is just 1.
Yeah, so the magnitude is 1 for a unit vector. And in general, a vector has like a magnitude, like how big the thing is, and some direction where it's pointing. So unit vectors only describe direction. It's only pointing at certain things. So there is a unit vector, like we could figure out what this, I'll call it like EP. There's a unit vector that points along that EP, right? We could take the magnitude of like its total distance from origin to point P, sum up all the squares, take the square root, divide all the points, and now we have a unit vector that's describing like direction. And I could say RP slash O is this distance R along EP. And it's still the same vector, it's just describing it in along a different unit vector. So that's the one thing that I want to encourage you to like try this out. Try using that kind of notation more often, of like explicitly saying like it's this unit vector, this magnitude plus that one times this magnitude, and it helps kind of organize where everything is pointing and all that. Especially as things start rotating and moving, it gets easier to keep track of things. Make sense? Was there a different approach? These were just the two things that I saw. It was like either parenthesis or something. I've also seen like either brackets, like X, Y, and Z, or X, Y, Z, something like that. Like all of these are fine, but it helps to write out like what coordinate system are you working in. And then even here, I would write out like, hey, this is coordinate system I. So if I'm moving on the X direction, it's X along that I coordinate frame. Nothing mind-blowing yet. Not yet. So we just did our first like kinematics problem. It's pretty exciting. Then I think, yeah, next one down here. Oh, not this one. So we want RPO, RPQ, and RQP. What do you think these are? What do those look like? And here we're trying to draw like little arrows to represent like what is RPO, RQP. This one, all the right concept, but just the negatives. Yeah, so the way to read it is the position of Q with respect to E. Yeah. Yeah, exactly. Okay. Oh, and you're doing this one's kind of like a I mean, mathematics and geometry. If you have like OP like that, which one of those vectors? Oh, I guess you do PO. Okay. Yeah, and so this is I have seen that notation like origin but now like this textbook old letters are vectors and then the subscripts are where you're going to find what yeah. Oh, you've never seen it? Well, I've never seen it. Yeah, exactly. Yeah, it was the start. Yeah. All right. That's what I was trying to figure out. All right. So, talking to a few people so far. Is this the notation that you've seen before of like P from O or something like, or sorry, OP. Is it OP? OP. This is because at least some people coming from like statics, this is the notation that they remember of like, where did I start? Where did I end? And there's an arrow saying I went from one to the other. We're gonna throw that out because even within that statics textbook, later on it goes into this kind of format, but I don't know why. I don't know why we have to keep like flipping the sign of things. Like thermodynamics drives me crazy because work is negative or positive, whether you're talking about a heat pump or a refrigerator. It's like it's the same thing. It's just one is doing work, the other one's getting work done. But anyway, okay. So instead, what we're gonna do is say RP/O. The way that I read this every time I see this notation is the position R of point P with respect to O. That's what this notation, and yeah, mathematicians and physicists love to condense everything to the point where it's almost unreadable, but that's what this quick notation means, is that I'm looking at where is point P with respect to point O. So you write where you went and then where you came from. All right, cool. So then we probably have, let's do a blue. Probably have a good handle on this. Which one is red, the P/Q or Q/P? What do we think? Who says the red line, the red arrow is P/Q? Yeah. P/Q. Yeah. Yeah, it has to, it takes a little bit, readjust. All right, R of P/Q. Cool. So then the other one has got to be Q/P, right? At least I would think so. What's relation between PQ, RQP, RPQ? Are they connected to each other somehow?
Only the direction.
The direction? Yeah.
Yeah.
Not the magnitude?
Well, don't they have the same magnitude?
Same magnitude, right? Yeah.
Yeah, same magnitude.
Yeah, so they're both, whatever distance it is to get from P to Q, it's whether you go forward or backward, it's the same distance. And they have equal opposite directions. So we know that RP/Q equals negative RQ/P. So I could have just shown one vector and then said equals R negative QP to say flip the direction, and I'm good to go. This one, it didn't ask us for this, but I'm wondering how much you remember. Right now I have like 3 vectors up there. If I want to know, like let's say I know what RPO and RPQ are, or let's write them down, right? Let's make some stuff up. Let's say RPO is, I don't feel like doing 3 dimensions, so we're going to say it's 2i plus 3j. RP/Q is negative 1i minus 1j, and then R let's say I know those 3 vectors, like I have the values, I measured them. Is there any way for me to figure out what RQO is? What is RQO? And here I simplified everything down to 2 dimensions. It's easier for me to work that way. What is RQO? Is it related to PO or PQ or QP, any of those? Yeah.
You find the coordinates of Q from P, and then do that from to Q.
Okay, yeah. So what would that one look like? And here, let's draw. So in this case, I go 1, 2, 1, 2, 3. P with respect to Q, so Q to P. So 1 and 1. I think I flipped what I was trying to do. 3i plus 4j, 4j, something. Like, what are we doing here? Yep. Distance, yeah, if we want like total distance, yeah. So and this was what I was wondering if you've seen or you've used before, but if I already have these vectors, I can go like tip to tail and add them up to get to that other vector. So this RQO is R of PO plus R of Q slash P. So in this case, I could say that R, in this like little made up example, RQO is 2I plus 3J plus 1I plus 1J. And they're all magnitudes and unit vector. I can add unit vectors to each other and still the same unit vector. So in this case, I would have RQO equals 3I plus 4J. Something like that. But I can always, if I'm kind of adding vectors up, I can add the magnitudes along the same direction. That's what I was trying to get at there. This one, you're not actually asked to do this in the homework, but I'm just trying to gauge like where we're at and versus where we're going with stuff. So we're going to need these like relative positions, relative velocity, relative acceleration, like all these terms. It's the same kind of vector formulations like this. Cool. If I know PQ equals negative QP, so position of P with respect to Q is the same but opposite as Q with respect to P. What about their speed? What about their velocities? Do I know anything about the velocity between them? They're equal opposite. Why? Why do they have to be equal and opposite? Because you multiplied by -1 to get the other one. This one, yes. Sorry, just if you guys see a chat pop up, let me know. If I take a derivative of a position, what do I have? Velocity. So if I know the positions are equal opposite, then if I take a derivative, their velocities have to be equal opposite, just based on like the geometry of how these things are measured. Kind of cool. And this is all like, again, extra information. We already did the main problem, like sketch and label vectors. And that's chapter 1. Ready for some kinetics? Do some chapter 2 work. So far we did kinematics, of just figuring out geometry. How do we describe position? Usually vectors. Velocity is going to be all vectors because it's derivatives of position. So now we'll jump into chapter 2. big. So I know it's tempting to draw the eye candy, the big muscly guy in this case. But the problem that we're trying to, oh, not that one, trying to get here. The problem that we're trying to answer is draw a free body diagram of the barbell. So not the hulking, like shirtless muscle guy, but just the barbell, the thing that he's holding. It's like, really, we need some, like, a mask over that. So not that guy, just the barbell, what he's holding. I want to see how you kind of approach this problem.
Oh, okay. Yeah. Of you? Yeah. Maybe this time. Yeah. Okay. Is there anything else? Is there a difference? Yeah. Okay. Yeah. That she's using force to like hold it up in the air. Okay. There's like the force to gravity or so like well, if it's just holding up the air, then it's just the gravity, like gravity on the barbell without anything else. Yeah. Oh, so it'll just be on the ground. Yeah. And then even then there has to be something preventing yourself. Yeah. Yeah, so that was my question. Like if you're saying it's not moving, then it's
All right, so I'll draw. There we go. Yeah, next week. So we still have time to like go through the rest of the problems. What was the other thing? I saw something else. Oh yeah. Did anybody have something different than these? I didn't see like everybody's free body diagram, but were there other approaches that you were thinking about? Yeah.
I just feel like a big, like, force just going down, like big force of gravity going down the middle.
So just
the center of that, yeah. That's
so just like so it'll take a second, it'll catch up. So just one weight pushing down?
yeah.
Okay. So nothing so the weight this would mean that the weight lifter, so I call it like FL, like the force of the lifter force of the lifter is 0, what happens then? Yep.
I was gonna say, there should be a normal force there.
A normal
There
force?
should be a normal force going out against gravity.
Is it, where is that one coming from?
It's coming from the ground up stacking into.
Okay, yeah, so if the lifter puts the thing on the floor, then now barbell sitting on the floor, and we could say so if this barbell is like in contact with the floor, then yes, the floor is applying normal force. But if the lifter is holding the thing, and we were talking about this a little bit over here about like there's definitely momentum. Like it's hard to lift things, and it's hard to lift them faster than it is to lift. Well, it depends, right? Like if it's already in motion, then it's easy to keep it in motion. But if you're trying to like accelerate the thing, that's extra work that you're doing. Like it's extra force that's needed to accelerate it. But the forces that you can apply, there's still only this. Like you're still limited to like, you can only have one resultant force up. You can add them together. You can keep them separate and look at how one affects the other, but you're kind of limited like how you can apply the force. Unless you're also like feet plus hands or something, like trying to juggle this thing. If you're changing how you're holding it, then that's different. Is one of these right? Or sorry, are any of these wrong between these? Yeah. That one, yeah. So and we talked about it in the back a little bit. Like, shouldn't there be something preventing the plates from falling off? Like if we're considering like barbell of just the bar itself, then maybe the weights, they are applying weight onto the bar, but there's got to be something preventing them from sliding off. At least hopefully, if you have a good spotter, you're preparing. So that would be like something so that even if it rotates, it doesn't slide off. Yeah.
I like the middle one. Can you just combine the two W1 and 2 to like one?
Yeah. Take the resultant. Yep. And then we end up with like W is W1 plus W2, right? So really, like all three of these are saying the same thing. Like we're looking at the same system. It's just we're breaking it into smaller and smaller pieces. Why would I want to do that? Like why would I put more work into a free body diagram like that? Yeah.
Is to like make it look more accurate.
Okay. Like maybe there's a question of accuracy. So adding more forces, does it become more accurate? Like will the fact that I split this into 2 weights versus 1 W, do I know the weight of the bar better now? Maybe not.
I would say it depends on what you're trying to analyze.
Depends on what we're like, what's the question that we're like really trying to solve here? Did you have a similar?
I mean, I was gonna ask like, would I be wrong to assume that the weight was and therefore be considered one object?
Yeah, that it's all kind of, so like in this first one, just saying like it's all one point mass.
Yeah, so I did that. I had 2 reaction forces. I had like 1 weight force.
Oh, yeah. So that was the other one. So there was a different approach. So combine the weights, but keep the hands separate. Yeah, and that's totally valid too, of saying like, look, my total weight is in the center of mass of this thing, and my hands have to apply, if they're equally spaced, equal forces, equal and 1/2 weight. Yep, that's another way to do it. So depending on the question that we're trying to solve with this, so one question might be, what is the load that each hand sees? And for that one, this free body diagram that we just put up, that's perfect, right? Because now we have two forces we can solve for both hands. If the question is, how much force does it take to lift a 100-pound weight? It's this one. It's got to be equal opposite, right? Like if we want to lift 100 pounds, we need 100 pounds. So that's all we need. And I know we're out of time. So have a great weekend. We'll come back. We'll keep doing more like free body diagram stuff. And we'll have more fun. Yeah. Yeah.